Alright, hey SPH3U, this is video number 7. It's about nuclear applications and kind of building off of the nuclear nuclear energy concepts we learned about in the last video. Here's what we're going to talk about. We're going to talk about ionizing versus non-ionizing radiation. No, your cell phone won't give you cancer because it's not ionizing radiation. So we're going to get that out of the way right away. Next up, nuclear medicine, so radio tracers and radiation therapy. So all those fancy machines that they have at hospitals. Then we'll talk about detecting radiation, what kind of stuff is used to detect radiation, and then protection from radiation, like radiation sickness and exposure limits and why they exist. So let's get started. Let's jump right into it with nuclear applications. And here I've just got a random thing I pulled off of a website, the Very Well website, talking about how to prepare for a PET scan, which is positron emission tomography. I picked this to start off with because this little box here, the IV delivers a radioactive tracer. So they literally inject you with radioactive material when you're doing a test like this, and that's what we're gonna kind of get started with. But first, a very important public service announcement about ionizing radiation versus radiation. When I say radiation, when I, in this lesson, I'm going to say radiation, I'm going to mean ionizing radiation. Oh, the end got cut off there, whatever. So yeah, when I say radiation, ionizing radiation. And the difference here is, ionizing. Ionizing means to make ions. It means that it can hit a molecule and take off an electron. Actually take off an electron. And because chemical bonds are made out of electrons, removing the electron breaks the bond, and it'll damage things. In particular, it can damage the DNA, which is what we want to avoid. If you damage the DNA, you can have genetic issues, especially in like a baby that's just starting to have the cells divide. So that's ionizing radiation. Everything below this red line here is non-ionizing. So you see radio, infrared, microwave, visible light, some of the ultraviolet spectrum. So all of these don't have enough energy per wave to break a bond, to make DNA damage happen. These ones do. So X-rays and gamma rays are ionizing. Everything else here is non-ionizing, which means that your cell phone, which operates in the microwave range, or like GPS satellites, or your Wi-Fi, which also will operate in the microwave range, they don't have the power to break any bonds. They don't have the power to cause cell damage in that way. So, your cell phone's not going to give you cancer because your cell phone can't mess up your DNA. Your microwave, though, can cook you. So with enough power, infrared and microwave can burn you and things like that, but they're not going to do it by DNA damage. You're not going to get proper radiation sickness. You're just going to get cooked, basically. So that's that. Let's talk about some different types of what we've talked about as radiation. We have alpha particles, which are helium nucleus, 2 protons, 2 neutrons, and they're just flying away very quickly. We have the beta, which is either a high-energy electron or a high-energy positron, depending on whether it's positive or negative decay. Right? A neutron turns into a proton. The negative charge has to go somewhere. That's beta negative. A proton turns into a neutron. The positive charge has to go somewhere. That's beta positive. Gamma is an actual ray. It's an actual wave, an EM wave, just a very high-energy one. And neutrons are also considered a type of radiation. The neutron flux, it will come in and just kind of deposit kinetic energy all over the place, which is pretty great. You might have heard of power lines. People worried about power lines in their backyard. Well, they're also radiating, but it's extremely low frequency. So like 60 hertz, I think. Very low hum. Out of the 3 common types of radiation that we learned about, which is alpha, beta, and gamma, which are back here, right? Alpha, beta, gamma. Only gamma is an actual ray. It's actually an EM wave, can be like actually literally called radiation. The other ones are still called radiation because they ionize. An alpha particle hitting a bond will ionize it. A beta particle hitting a bond will ionize it. But they're not actually waves. They're not radiating. They're just going in a straight line. And yeah, they're just particles. So this error, the fact that alpha and beta radiation are actually made up of particles, is historic. They discovered radiation before they discovered electrons. So yeah, so interesting. That's Henri Becquerel. You can look him up, Henry Becquerel, in English. He's the one that's credited with the discovery of radiation. Got a Nobel Prize for it. Yeah. Anyway, so the important thing here is what is ionizing radiation, and it's the high energy stuff. Essentially, the higher energy the wave, the closer together the waves are. The higher the frequency, the closer together the waves are, and they become close enough together to actually hit those electrons, to actually hit those bonds. When they're far apart, the whole chemical just kind of flows over the wave, but the high frequency waves will hit. Yeah. All right. Next up, first thing now is nuclear medicine, right? So that's our goal: nuclear medicine, radio tracers, and radiation therapy. I'm going to pause and fix up my little current topic and keep in mind. And we're back off pause. Radioactive tracers. These are used to visualize kind of molecules in the body and in other things. I'm actually going to move my. There we go, move down. And this is a picture of it. Here's a proton decaying to a neutron, and when a proton decays to a neutron, the positive charge has to go somewhere. Out comes a positron, which is like a positive version of an electron. That positron is actually antimatter. And if it hits a normal electron, of which there are a bunch everywhere, right, even in the air, it'll annihilate and make two gamma rays, one going one way, one going the other way, in perfect opposite directions. And that comes from E equals mc squared. When these two annihilate, literally the mass disappears. The energy from that mass has to get carried away, and that's the gamma rays. So you just need to find something that has too many protons rather. So fluorine 18 is a common one. It decomposes to oxygen 18, which is stable. The half-life there is only 2 hours, which is good. We want a short half-life, because if it's a short half-life, it won't stick around in your body. So what they do is they take a sugar molecule, this is a normal sugar molecule, and they just stick fluorine 18 on it. And when it's in your body, it'll go wherever sugar goes, but it's also radioactive, so they can scan your body and pick up the radiation that these are coming off of. The radiation that these are giving off. So the detectors are all around, and what they detect is these two gamma rays, just called, and they're very, very, very sensitive, and they can actually trace it right back to the pinpoint location where they came out. And using that, they can build like a 3D model of where the radiation is, and where the radiation is where this molecule is, and where that molecule is where sugar is. So here it's actually showing where there's a lot of sugar uptake in this particular person's body. You can see a bunch of it in the brain, because the brain is always using lots of sugar. Then there's like a lot of it where you don't expect it. This is the rectum back here. So this person has colorectal cancer, because there's a bunch of sugar being used down here where normally it isn't. And there's also a bunch of extra sugar being used here in the liver. So where I took this website from, I believe it was just Wikipedia, it's a GIF on Wikipedia, was saying that this person has colorectal cancer, and the scan is showing that the tumors have metastasized up into the liver. Yeah, it's pretty neat. Here's them injecting the dye, the radioactive tracer. It's actually a shielded syringe, which I thought was really cool. It's like wrapped in some kind of thing that'll absorb the radiation, so that the doctor doesn't get a bunch of radiation going into their hands, because the doctor has to do it a lot of times. Meanwhile, the person only has to go through the test, once. So this is a PET, a positron emission tomography scan. The positron is this thing. The positron emission because this thing is emitting the positrons. It's emitting the beta positive rays. And tomography is just a fancy way of saying we combined a bunch of individual scans and made a 3D image. Another very common radioisotope, aside from fluorine-18, is this one, technetium 99M. The M stands for metastable, meaning that it's actually a higher energy than it wants to be. It's higher energy than it can be. So every 6 hours, half of it decays down to normal technetium. So from technetium 99M to just technetium. And it's only a 6-hour thing. It's produced often in particle accelerators. But because it's a 6-hour half-life, you can't really get it from the particle accelerator to the hospital in time to be useful for the scan. So instead, they take this stuff, molybdenum 99, this stuff, molybdenum 99, and that decays down to technetium 99M. The stuff that makes that far more kind of available is nuclear reactors, old nuclear reactors specifically, and they make large amounts of it rather than in a particle accelerator where you can't make that much of it at a time. The molybdenum from the nuclear reactors, there's a lot of it. Here's a thing from Wikipedia of the different sources, and you can see here that Canada was actually a major source of it for the world, the entire world, at one time. But now that's been decommissioned, and we're left with a bunch of other ones. And look at these years. These reactors first started up in like the 60s and 70s. And there's one from 2006, but that only produces for Australia. So yeah, not great. When the Canada reactor actually got decommissioned, they had to shut down unexpectedly, and it really affected the world supply of this very important radioisotope. So I'm not sure what their plan is once these reactors get too old, but they're going to need to figure out how to get more of this stuff. The molybdenum 99, I think, has a half-life of something in the range of 4 days. 3 days? Yeah, something like 3 days. So it's a much longer half-life than 6 hours, and so you can actually transport that, hop it on a plane, bring it to the hospital, and then they've got a source of this technetium stuff for, maybe a week, and they'll need another shipment. Something like that. Yeah, and here's just a picture of a molecule with that radioisotope in it, the radioactive technetium in it. Okay, so that's the first kind of nuclear medicine, is just tracing things using radioactive tracers. The next kind of nuclear medicine is radiation therapy for cancer cells. I call it therapy because what we're really doing is just killing. We're just zapping those cancer cells. Here's a person that's showing off a small tattoo, a little tiny blue dot. It really is just a single dot. They make this tattoo at the hospital, and they don't use like a tattoo gun for it. Although some people do kind of make fancy designs around their dot, and they get their tattoo artists to like make cool things. But literally, they just put the tattoo ink on the person's skin and just go poof with a needle, and that makes one single dot. That dot is to target the laser. That dot targets this thing. And this is a radiation source. It's a beam source. That's called external beam radiotherapy. This thing has some way of generating radiation, and the radiation can either come from an actual radioactive isotope, or it can just be generated on site from an accelerator that's built into the machine. There's a few different ways to do it. And the beam will come in and hit the person, and it'll go right through them. And their body will absorb the radiation, and because it's ionizing radiation, it'll break chemical bonds and cause cell damage in there. But they're clever. What they do is one shot through the body won't do a lot of damage to any of the cells in there, so they rotate the beam. They shoot once like this, then once like this, then once like this, then once like this, then once like this, and you get, dozens of beams coming in, all of them focused around the tumor. So the tumor gets the tumor sees every single beam, but the rest of the body doesn't see every single beam, and so you get you get more radiation to the tumor, more cell death right where the tumor is, and less cell death around. That's the idea behind radiotherapy. It means that people that are in this machine have to be held very, very, very still, and it's generally thought of as quite uncomfortable. There are new machines that can actually kind of adjust and track the tattoo in real time and things like that. There's a lot of interesting innovations there. I've got a video, you'll see it in the description, of one of these machines at work, and you'll see it and then move around and go. You don't see the beam, like that would be super cool if you could, but no, you don't. The other type is called brachytherapy. This is sometimes done with lung cancers and cancers that are easily reachable through the windpipe or through big blood vessels, where they can actually insert a tube that's holding a little radioactive pellet, and then they put the pellet right next to the tumor, right where the tumor is. And then they leave it there for a certain amount of time. You know, there's a radiologist that will work out, not a radiologist, sorry, a nuclear medicine technician that will figure out exactly how long to leave that thing in there for, until the tumor gets enough radiation, and then they'll pull it back out. The idea here is that the radiation is strongest right near the source, and then it kind of fades as it gets further away, kind of like the light from, you know, a light source. So the tumor gets most of it, and the rest of the body gets less, and that's the idea. Yeah. So yeah, that's what this is basically saying. It's just you're moving the beam in order to really focus on the tumor, and here you're just basically sticking the radio source right next to it. So lots of different sources. You can just have radioactive isotopes in a little can with a window. You can have an actual accelerator on site. Sometimes it's just straight up protons. They just accelerate protons and hit people with ionizing protons, which is a more modern version of radiotherapy. Other times it's just one of these, just a chunk of like cobalt or something in a can, and then they rotate the can, radiation comes out, and then they close the can, and no radiation comes out. It's just trapped inside the can. So that's the idea there. There have been a couple of incidents where hospitals have been decommissioned and people go scavenge in the hospital like wreckage, and they find these radiation sources. And there have been at least two different accidents that I know of where there was accidental radiation exposure, and in the scrap market, people actually died from radiation poisoning because they would steal these out of hospitals and crack them open to see if there was anything interesting inside. Yeah, I'll put a link to one of those down below, one of the really sad ones in 1987. A bunch of people got exposed. All right, so that's that. We're moving on to the next thing, which is detectors that use radiation. So detecting radiation. I'm going to pause so I can fix this stuff up just a sec. Okay, we're on to detecting radiation. We've got two sections here. There's detectors that use radiation and then detecting the radiation itself. So to keep in mind here is ionizing radiation can affect electrons directly, and when it does, it's going to lose energy, and the electrons are going to gain energy, essentially. So the first type of thing, you might have heard that smoke alarms are radioactive. Well, they are. There's a radioactive americium source inside it. Americium is the element there. Americium emits alpha particles. Alpha particles are just these big chunky, where's my alpha particles? There's an alpha particle. They're these big chunky helium nuclei. And so they basically, the first thing that they hit, the first relatively solid thing they hit, they dump all their energy into it. So in a smoke detector, normally there's this radiation source and it's coming up and it's hitting a detector. But if smoke particles are there, the smoke gets in the way, it blocks it, and then the detector goes, there's no americium, there must be something in the way, and it assumes that that's smoke, because it's tuned, the americium is very good at ionizing the smoke, and then it sets off the alarm. That's how the test button works. It just blocks the the americium source from the detector. It blocks the alpha particles from hitting the detector, and then the alarm goes off. It really does think that there's smoke in there, or at least it thinks that the thing is blocked, and then it sets off its super loud alarm. So that's a smoke alarm. We're actually looking for things blocking the radiation. Same thing here when we have this is a scanner that's actually using gamma rays to scan vehicles that are coming into the Super Bowl. It can go right through the vans and right through the people and stuff, and it's a low dose, low enough that people don't really have to worry about it. But it can go right through, and based on how it absorbs, you can kind of tell a little bit about what's inside. So in this case, they're probably looking for a van stuffed full of something to, maybe it's an explosive or something like that. That's probably what they're looking for there. It's also used industrially in industry. You can use radiation. You know how thick something has to be to absorb a certain amount of radiation. So you send a beam through and see how much of it makes it out the other side. And then if it's thick enough, it's attenuating enough of the radiation. So, a lot of it comes in, and a little bit comes out. A lot comes in, a bit comes out. If it's thicker, less will go. If it's thinner, more will go through. And you can kind of tell how thick something is and how well you've made it by just sending radiation through it into the other side. This is something called non-destructive testing. And as you can imagine, a lot of people like the idea of testing a built object without destroying it. So radiation tests are one of the ways that can happen. So that's detectors that use radiation, including the non-destructive testing apparatuses. Next up is actually detecting the radiation itself. So ionizing radiation affects electrons directly, and that's how the Geiger-Muller tube, the Geiger counter we might call it, works. Basically, it's almost like when you have a balloon, and or you rub your feet on the carpet and you get a shock when you touch the metal door, but only when you get close enough. The electrons are in a high energy state, and they want to jump away from you and into the doorknob because you've kind of charged yourself up. And so they jump to the doorknob. Here, the same kind of thing. The electrons on the outside of the tube really want to come down and hit the little blue anode here. They're charged. The tube is charged, and they can't normally do it. But if the radiation comes in and hits that electron, it kicks it up just enough energy to jump over. So that's the ionizing radiation can affect electrons directly. The radiation gives it enough energy to just hop over, and as it hops over, just like when you get a little static shock from the door, and sometimes you even get a sound, you get this little ionizing kind of cascade through the gas that the tube is full of, and that comes out as a little electrical signal because an electron has jumped, or several electrons have jumped, and the thing records that as a crack, one of those little clicks that you hear on the detector. So that's the Geiger counter. Another design is the scintillation detector, where the radiation comes in and hits a crystal. The crystal creates light in response because the energy has to go somewhere. It just turns into a light energy. And then it comes in, knocks an electron, because that's what radiation does. It can affect electrons directly. And it goes through this thing called a photomultiplier tube, where the light amplifies along the way, and then that hits a measuring device, and that gives you a little click, just like the Geiger counter click. So two different types. That's how radiations work. These are both active radiation detectors, so they only detect radiation that is currently there, and other times you might not want the current radiation level. You might want the total radiation level that something has gotten, and that's something called a dosimeter. It measures the total radiation dose, or accumulated radiation dose. There's a few different kinds. There's digital ones that'll just count. It's like a Geiger counter that's attached to a computer, so it just counts how many clicks there have been. But the other one is just badges, and these badges have certain chemicals in them that kind of react to the radiation, and the more of the chemical that has reacted to the radiation, the more you assume the dose is, the higher the dose gets. So that's that. I actually had something like this in my house recently because I was testing my house for radon, which is a radioactive gas that is sometimes common in different places, and so I wanted to test to see how much radon my house has. So I ordered this test kit from a company, and I had to put it in in a place, leave it alone for like 6 months, and then send it back to the company in an envelope. And then they told me, oh no, it was fine. The dosimeter didn't detect a high enough dose to be worried about. So you're good. So yeah, apparently my house doesn't have a lot of radon in it, which I'm happy about. So yeah, that's detecting the radiation with dosimeters or active detectors, and they're based on that same principle that the ionizing radiation can knock electrons away from things, and in the process releases energy that we can detect either as the actual electron cascade or just as light. Next up, we've got protection from radiation, which is another one of our things, right? Protection from radiation and radiation sickness, the last piece of what we're going to talk about here. So I'm going to pause again and fix things up. Okay, so last thing is this protection from radiation, from irradiation. So how to stop yourself from getting irradiated. The important thing is here, and keep in mind, is that different types of radiation have different penetrating powers. So here's a kind of useful guide. I'll have a link to this person's website down below. He does a lot of cool physics guides and chemistry guides. So I'll definitely shout out to Compound Interest, who shares this stuff for free with everybody. This is different types. So alpha, beta, and gamma, as we talked about. Alpha is just a big helium nucleus flying through the air. It has a very high ionization ability because it's huge. It's big. It's carrying a lot of kinetic energy. Right? Remember from the energy. Well, we're in the energy unit. More mass means more kinetic energy. Beta, electron, also coming in with mass. Nowhere near as much mass as the alpha, but often coming in faster. Not as much ionization ability because when it hits a chemical, an element, or an electron, it doesn't deliver as much energy with the blow, but it can penetrate further because it's speedier, it's faster, so it can and smaller, so it can kind of like wiggle through the gap between things, whereas the alpha particle just gets completely stopped by, say, a sheet of paper. Or, if you will, the gold foil in Rutherford's gold foil experiment, if you remember that from chemistry. And then gamma is actual EM, right? Gamma is the only one that's actually a radiation, like an actual wave. And because it's a wave, it'll punch straight through a lot of different things. Think about like how sound waves can get transmitted through like a car window and things like that, and someone's driving by with really loud bass, you still get the sound out. The gamma, because it's light, can actually just right through until it gets stopped by something. Often lead is used to stop gamma and x-rays. That's why you have to wear the big thing when you're getting an x-ray to protect the rest of you. Typically, the higher the ionization ability, the lower the penetration. This should make sense to you because if it has a really high ionization ability, it's just going to hit the first thing, and it's going to ionize that first thing. If it's got a low ionization ability, it can go further before it ionizes something. Just know this. Know the spread, that alpha is the most dangerous, but also the weakest in terms of penetration. Gamma is the least dangerous as an individual thing, but it penetrates much further. So a strong gamma source can get you even, through a wall and stuff like that. Alpha, meanwhile, will get stopped by a few feet of air or just a piece of paper and things like that. This is one of the issues with smoking, actually, because when you smoke, the smoke has radioactive stuff in it, and it's sitting right there next to your lungs. after you inhale, and so you're getting a very concentrated dose of alpha because it's right there in your cells, or right next to your cells, and so you're getting all of this power because it's already inside you. It doesn't need to penetrate. Meanwhile, gamma, you can't really avoid it, and beta will go through your skin, but that's fine. It's not super strong. So, quick question then: why are gamma emitters preferred for radiation therapy? Remember, in radiation therapy, they would use a radiation source, and you think about it for a little bit. Gamma, it's got low ionization ability and big penetration. This is exactly what you want for a radioactive test. You want something that leaves the body very quickly and doesn't deposit its energy in the body. You want it to hit your detector, right? So if you have it starting inside you, you want it to leave. And the ionization ability being low is actually a bonus there because that means it won't ionize inside of you. So typically those radio tracers, I guess it should be actually radio tracers, right? Radio tracers, we prefer gamma emitters for that. Same thing, I guess, with the radiotherapy, because you're sending a beam through and then through and then through and then through and then through. You don't want the rest of the body to get too much of it, so I presume that high penetration is probably good for that. I'm not a nuclear technician. I wouldn't know, but they probably have to make a decision on what kind of radiation to use. Yeah, so if you remember, your smoke detector used alpha particles. Very low penetration, very high ionization ability. And that just gets absorbed by the smoke detector itself. So, yeah, you don't have to worry about your smoke detector having radioactive stuff in it. Just a piece of paper will stop it, so the plastic of the smoke detector will obviously stop it. But gamma rays from space or even from radioactive stuff in the ground can make it all the way to us on the surface. So if you live in a place with a lot of granite and a lot of bedrock that has uranium in it, you're actually getting extra radiation just from that, and you can't avoid it. You can't avoid the stuff coming from space either. I'm getting radiation right now from the cosmic rays. They're just hitting me. It's fine. And we absorb about 4 millisieverts per year from natural sources. That's just a radiation, a measure of radiation. And just as a kind of guideline, about 50 millisieverts per year is considered safe for radiation workers, like people that work in actual nuclear plants. So 4 millisieverts it's fine. Other interesting things, because the air will absorb radiation when you're on a flight, like a transatlantic flight, you actually get a solid amount of millisieverts, right? About a 40th of your yearly dose in one flight. It's actually about 5 times more than a chest X-ray. And because of this, the public radiation exposure is limited to, I think, an extra 2 millisieverts per year. But air crew are actually considered radiation workers in a lot of laws and regulations. They get a higher exposure limit. In the EU, it's 6 millisieverts. In other places, it's 10. Yeah, it's kind of neat to think about. Here's the sources of typical exposure, right? 360 milligram, which is, about that 4 millisievert thing. Cosmic rays is about 7% of it. Natural radionuclides just inside your body already, like the carbon and potassium stuff inside you that's radioactive, because some proportion of it is 11%, so you just can't avoid it. It's part of your body. It also means that you get radiation when you hug somebody, because you're close to their body, and their body has natural radionuclides in it. Terrestrial radiation, just from the Earth, about 8%. Consumer products, so stuff you put on your skin and stuff, about 3%. Nuclear fuel cycle, if you live near a power plant, you're getting a tiny bit of extra radiation. And then medical, so any x-rays and stuff, just the average person gets, X amount of x-rays per year, and that adds up to about 15% of the radiation dosage. And then look at this, the biggest one, radon, inhaled radon. Radon is an alpha-emitting gas. It's a noble gas, so you can't smell it, see it, you can't detect it at all. It doesn't react with anything, so it's very, very hard to detect aside from its radiation content, and that's why I had to test my house for it. Yeah, mine came back fine, or within limits anyway. And it's an alpha emitter, so you breathe it in, and it's in your lungs, and it's emitting alpha. But thankfully, most houses don't have a lot of it, and it's fine. It's totally within normal limits. Remember, radiation workers in nuclear power plants is 50 millisieverts per year, and all of this together adds up to about 4. So, not too bad. But do get your house tested for radon if you haven't recently. That's something that the Canadian Nuclear Council really suggests for people. Yeah. So what happens if you do absorb too much radiation? That's our last piece here. It does damage. All ionizing radiation can do damage to your cells. Eventually, they heal that damage. Over time, your body heals that damage either by repairing the cell or just destroying the cell and putting a new one in its place. Whatever. It's like getting a sunburn. You just heal it off. But over a short time, if you get a lot of radiation over a short time, too much damage, especially in one place. And so you'll get radiation sickness, and the cells will start dying en masse. The severity depends on what part of the body was affected. So here's a few kind of dosage limits from various things. So the state of Connecticut, for example. The whole body, 1.25 rems per quarter or 5 rems per year. But if it's the head, or if it's the hands and the forearms, or the feet and the ankles, so like just the outside here, where it's just, it's just bone and muscle and stuff, there's nothing really vital in there, nothing that's gonna, like cancer there isn't going to like really screw you up. Also, they regenerate a lot. It's like 20 times more, right? Skin actually also has a higher exposure because your skin is constantly regenerating itself, so it'll heal off the damage faster. And then you go down to, so this is 5 rems a year, but if you go down to the fetus, right, if they have a pregnant radiation worker, she has to watch out and watch out how much dosage she's getting, because about 1/10 of that is the limit for a fetus, just to protect the developing fetus, because it's actively dividing its cells. So any kind of mutation from the radiation, will propagate through more of the baby as it grows. So yeah, they really care about how many you get when you're pregnant. Same thing with pregnant women; they're typically discouraged from getting X-rays and stuff like that because of the effect on the baby, or at least X-rays that will hit the womb. Here's another one with an annual dose limit. You can see that the whole body, 0.05 sieverts, the same 5 rems, or 50 millisieverts. But 5 rems for that. The eyes can take up to 15 rems. The skin can take up to 50, so 10 times more. Elbows and hands can also take up to 50, so also 10 times more, and same with knees to feet. But the vitals, where the lungs and the heart and the liver and all those guys are, can't take as much. Then over here we have a kind of a chart of radiation sources in millisieverts. Starting with a dental X-ray, I had one of these done recently, 0.01 millisieverts. Right, since we get 4 millisieverts a year, that's less than a day worth of background exposure for a dental X-ray. A chest X-ray, 0.1 millisieverts. So, we're getting up into maybe 5 or 6 days worth of background exposure. A mammogram is about 0.4, so 4 times more than a chest X-ray. Which is just because it's a more intensive check. radiation in Fukushima on March 12th per hour, right? Per hour. That means in 4 hours at the Fukushima site on that day, on March 12th, before the radiation had a chance to disperse, you could be there for 6 hours or 4 hours and get your entire year worth of radiation, in addition to your entire year worth of radiation. New York City to Tokyo, an airline crew, remember that the radiation workers, they can get up to 9 millisieverts a year just going back and forth from New York to Tokyo, because it's a big long flight and they're up in the upper atmosphere a lot more, and they have less protection from the air above them, so those cosmic rays are coming in. But even that is less than a full body CT scan, so you can only get a few of these a year, or else you go way over your limit very quickly. So yeah, just one CT scan. One scan is more than double your yearly background rate. Here's the limit, the 5-year limit for radiation workers. Chernobyl was a big accident in Ukraine, and residents of the nearby city of Chernobyl and Pripyat had to get, relocated. In the middle of the Fukushima plant, after it blew up, there were 400 microsieverts per hour, which, that very quickly went down. That was just while stuff was settling out, and then they went and cleaned it all up and put it in bags and stuff, and put it in storage. And after that, we get into the dangerous stuff. So over 1,000 millisieverts in one dose. Over 1,000 millisieverts in one dose will cause some nausea and some basic sickness. So you'll get a bunch of cell death, but you're not going to die. Your repair mechanisms will come in and heal you. That's 1,000 millisieverts. Remember that we get about 4 a year ish. If you get up to 5,000, that's just too much damage for a lot of people to handle, and half of people die in a month. 6,000 for the Chernobyl workers who died within a month, so it's about right. And then if you get more than that, it's fatal within weeks. Just absolutely fatal within weeks. I'm going to link this article, this one, about what's called the Demon Core. And this guy, Lewis Slotin, who was a nuclear physicist, and he was working on this core, a research core, and accidentally dropped it, and it released a bunch of radiation, and he died. But he decided to basically dedicate his body to science while he was still alive, because he knew he was going to die, and he let them do all kinds of medical tests and stuff on him as he was slowly dying from radiation sickness over a matter of weeks. Really cool story. Please read that. Really cool. Sad, but cool. All right, that is it. That's the whole thing. So let's review what we did here. We talked about ionizing versus non-ionizing radiation. Your cell phone won't give you cancer, neither will your Wi-Fi. Nuclear medicine, so radio tracers, radiation therapy, the idea of sending multiple beams in to hit just the tumor with the maximum amount of radiation, but spare the rest of it. Kind of the same idea as those dose limits, right? The tumor gets more dose and the rest of the body gets less dose. That's kind of the idea. Detecting radiation from scintillation detectors and Geiger counters. Detecting stuff with radiation, so like using it to inspect welds and materials and things like that non-destructive testing stuff. And then finally, protection from radiation, this idea of penetrating power. So you have to know that alpha is very low penetration but very high energy. It'll get stopped by a piece of paper. That beta is in the middle between the two. It can get stopped by a sheet of aluminum, but it will go through paper. And that gamma is depending on the energy, is the strongest in terms of penetrating power, but the weakest in terms of actual energy delivered to the electron or the bond or whatever it's going to break. And of course gamma is on a spectrum, so you can have high energy gamma and low energy gamma. and each one has its own penetrating power and its own strength. So that's it for now. Thanks a lot, and I'll see you guys in class. Bye.